over 2. So if acceleration is constant, they're equal to each other. If acceleration is constant, I also have that first cake formula over there. So where I have Vf, I can write Vi plus At. So this is Vi plus At all over 2. So just pulling stuff out, a little bit easier to see. I had displacement is equal to, if I multiply both sides by time, I get, well, if I add those together, I got 2Vi plus At divided by 2, and then times time over here. And then let's simplify it. So it's 2Vi over 2 plus At over 2 times time. But the most common not how math works thing I see here is people just canceling out the 2 and being done with it. We're dividing both things by 2. So over here, the 2's cancel out and I'm left with the Vi, and over here, I can't cancel the 2 out. And so what I'm left with, so then if I distribute the T, I have my displacement is equal to VIT plus 1/2 AT squared. And we have another cake formula. In that last problem, where we had my initial velocity being 40 meters per second, my final velocity being negative 19 meters per second, time was 7 seconds, and acceleration was 3 meters per second squared. So it should be negative 40. What was the displacement? Well, if it gets closer to 0, gets closer to the origin, then it should be, well, I'm going to retract that. So now if I want to know what the displacement is, I just plug and chug. Negative 40 times 7, so my displacement equals plus 1/2 3 times 7 squared. Negative 280. Plus 73.5. I think that's right. Okay, I got one acknowledgement. Am I done? All right. Now, I don't know if it's getting closer to the origin or not. All I know is from the beginning of this problem to the end of the problem, it goes in the negative direction, 206.5 meters. If it started on the positive side, let's say if it started at positive 300 meters, yes, it's gotten closer. If it started at negative 10 meters, it's gotten farther away. Tack on the next cake formula is that displacement is equal to VIT plus 1/2 C squared.
From there, you further simplify it down to where you see the final.
Whatever. Or wait, there's more.
Yeah, I'll wait there.
All right, let's take that next step. Recognize what average velocity means is just displacement divided by time. So I could have equally found my average. So So I had negative 40 plus negative 19 divided by 2 to find my average velocity. And let's clean this up some. So my average velocity is negative 40 plus negative 19 divided by 2. 59, so
Negative 28.
28 point, negative 28.5.
Should just be 28 now.
Oh, I added another second for that problem.
Oh, right. Yes, it is, 28.5.
Meters per second. And so that's my average over 7 seconds. So my displacement is just negative 28.5 times 7. And I should get the exact same answer. And if not, something's going wrong. But there's multiple ways to approach a number of these problems. We have negative 206.5. What do you got?
Negative 199.
All right, so obviously there's a mistake somewhere.
I think it should be negative 29.5.
29. Oh, yes, thank you. Which adds another 7. So 206. There we go. Thank you. Oh, should have jumped all over that. Missed the opportunity. Questions to hear? All right. Next. No, not that one, that one. Let's talk about dot products. I know you were thinking that might be a great way right before the weekend to do dot products, but let's do it now, sort of get it out of the way, relieve some of the just anxious anticipation of them.
Right.
When you're multiplying vectors, there's 2 different ways of doing it.
That's the multiplications.
That is more things than I wanted to write down. All right, A dot B. This is known as a dot product. I'm hoping you can guess why it's called dot product.
Because after the dot, you make the product.
Pretty much. As opposed to the other way of multiplying vectors, which is sometimes referred to as a cross product.
Oh, wow. Those are the sensory idiotic.
Now, dot products also have another name. They're sometimes called scalar products. Why do you suppose it's called a scalar product?
Oh, wait, wouldn't it be just, wouldn't it be a vector product?
No, this is a vector product.
I should have 3.
So somebody take a shot at why this one's called a scalar product?
Because, is it because, it would have a magnitude in a direction?
In other words, a scalar?
Oh, yeah,
Yeah, because the answer here is a scalar.
yeah.
And this one?
That's a vector.
I'm going to write down, I'll put vector in quotation marks. This is just, as, for the sake of this course, calling it a vector, absolutely no problem. There are some people get picky about it, and really it's called a pseudo-vector or an axial vector. This deals with some reflexive symmetry beyond the scope of the course. I throw it out there just mainly for trivia at this point, but this creates a vector. This we will get into in more detail in rotational motion, whatever chapter that is. This we'll get into in more detail. We'll do some of it now, but we'll do more detail when we get into work and energy. Chapter 7, I think it is. All right, so let's talk about the other big difference between them. If I'm multiplying 2 vectors, call that A and B, with some angle in between them. Recognize vectors have, I can break a vector up into perpendicular components. So if I break this up into a component along the direction of B and then perpendicular to B, so that's a right angle, I can multiply this length of B times either the part that's parallel to it or the part that's perpendicular. Well, cross products, if you think about it this way, the cross, they are perpendicular to each other. And a cross product, I'm multiplying the perpendicular components. With a dot product, I multiply parallel components. So this multiplies parallel components. And this multiplies perpendicular components. So, let's just do some numbers here. Let's make B, establish a convention here, I and J. Let's say that B is 5 meters I hat, and A will make 3 meters I hat plus 4 meters J hat. In other words, the part parallel to B is 3 meters. The part perpendicular to B is 4 meters. If I multiply the parallel parts together, I'm multiplying 3 and 5. So my dot product would be 15. And the units, since I multiplied meters times meters, would be 15 meters squared. Again, the dot product is a scalar product. There is no direction in the final answer.
Wait, where did you get the 3 to multiply 15 by?
I said that A was 3 meters I hat plus 4 meters J hat. So 3 meters in the I hat direction, 4 meters in the J hat direction. I just defined A to be that way.
Okay, so that's so you multiplied the 2 I hats together?
Yes. And as a matter of fact, that's a general rule. If I give it to you in rectangular notation, 3 meters I hat plus 7 meters J hat dot 4 newtons I hat minus 3 newtons J hat. Let's do a different number, 2. Really what you're doing is you multiply the I hats together and you multiply the J hats together. So that would be 12 Newton meters minus 14 Newton meters. Yeah, I'm multiplying meters times newtons. Or negative 2 Newton meters. Now the main reason I wrote newtons first, if you're doing multiple units like that are multiplied together, please make sure there's a dot in between. Although, if I wrote capital N lowercase m, it's not going to be confused with anything else. But if I reversed it, mn without a dot in between is not the same thing as m with a dot, n with a dot in between. This is meters times newtons. This is a millinewton.
Oh, wow.
A thousandth of a newton. So put a dot in between just for clarity. And I put newtons first just so that if someone accidentally forgot to put a dot in, they would not be writing the wrong unit.
Whoa. Physics.
What would happen on this problem over here? What would happen if I put them in the reverse order? Suppose I did 4 newtons I hat minus 2 newtons J hat dot 3 meters I hat plus 7 meters J hat. What would the answer be now?
Same thing.
Commutative property holds. The order in which you do a dot product does not matter. Unlike cross products. Cross products, it matters. All right, one last little bit with dot products before we get back to our cake formula. If I do I hat dot I hat, what would that equal?
I hat squared.
All right, technically, if you wrote I hat squared, it would mean the same thing, but we can do better than that. Actually come out with an answer.
Oh. An answer like a number answer?
Yeah,
Do like two on
not two. If it were two I hat, that means I've added them.
Pi I hat. Oh, yeah.
No. What? Yes. How'd you get one?
Okay.
It's a physicist, I think.
Because.
Just genius.
It's just glitchy. I think just like, a number by, multiplied by another number, just. Never mind. 'Cause
2 times 4, yes, 1.
All right, let's think about it this terms. If I did one I hat dot one I hat, and I multiplied the I hat components together, I get 1 times 1, just 1.
Do they cancel out? The I hats?
No, it's a dot product, they go away.
Oh, okay.
I hat, any vector, unit vector times itself is gonna, dot product with itself is 1. Any unit vector cross product with itself is 0. Because remember, if dot products were multiplying parallel components, well, that is definitely parallel to that, because they're the same thing. They are completely in the same direction, so all I'm doing is just multiplying the magnitudes, 1 and 1. If I did I dot j,
Then we have, oh, still 1. No, never mind. See, that's where you're wrong. Anyway, we would have.
they are perpendicular to each other.
We'd have IJ.
There you go.
I'm multiplying, the genius wore off. It'll come back. I hat and then j hat. Remember, I'm trying to multiply parallel components. How much of j is in the same direction as I?
None.
That is correct,
So
none.
it's 0.
So I could have actually taken our problem over there, the 3 I hat, 7 j hat, 4 I hat, negative 2 j hat. I could have foiled. This is the long way, but we'll get the same place. First, I get 12 I hat dot I hat. Last, minus 6 I hat dot j hat. Plus 28 j hat dot I hat. Minus 14 j hat dot j hat. That's just doing FOIL, first, outer, inner, last. I hat dot I hat, that's 1. I hat dot j hat is 0. J dot I, 0. J dot j, 1. And then stick units in. Unless I made a careless error.
Oh. That's awesome.
And since all the ones that deal with have different unit vectors will ultimately end up with 0, we just, in essence, we multiply the i's together, we multiply the j's together. If I did, and then the last bit before we get back to the kinetic formulas, a dot a, besides a squared.
What?
They're not unit vectors.
Oh, okay. Zero. Okay.
Only if it's a 0 vector.
Awesome.
I have a vector, and I multiply it times itself. How much of this is in the same direction as that?
All of them.
All of it. So I multiply the parts that are in the same direction. Well, if that magnitude is A and that magnitude is A,
I thought you said it was.
I was picturing A with the vector symbol over it squared, but, yeah, I misspoke. Sorry if that messed you up. It's just the magnitude squared. No matter what A is, whatever the magnitude of A is, if I do the dot product, that is the same as this. Sometimes a student will write A with a vector symbol squared. This is what I was saying. Yeah, that's not what I want right there. I just want the magnitude squared. All right, we are now ready to return. Questions before we return to the kinematic formula. Formula. All right. So what I'm going to do is I'm going to multiply acceleration and displacement. I know, it sounds crazy. It can be done safely.
Oh, we're definitely gonna blow something up.
Not today, not on my watch. All right. Acceleration is the change in velocity over time, so that is v final minus v initial over time. Delta x is average velocity times time. So I'm doing a dot product there, it's got that. And the dot product of vf plus vi divided by 2 times time. And well, the things that aren't vectors are just factors. They can come out. The times cancel out. The 2 pops out front. Matter of fact, I'm just going to cancel out the times because I'm dividing and multiplying. And that 2, I'm just going to multiply both sides by 2 to bring it over here. So again, 2a dot delta x is equal to vf minus vi, not vf